Okay, in this lecture we will study the introduction about the numerical computations. What is a numerical computation? So first of all we will study its definition, and its definition is that it is basically NC, or numerical computation, is the study of algorithms that uses numerical approximations or numerical methods for solving the problems of mathematics and being able to estimate the errors involved in it. So it is the tradition of practical mathematical applications or mathematical calculations. Alright, so this is definition of NC, and why do we need numerical computations? So many questions were arise that why do we need numerical computations if we already know the linear algebra, or if we already know the ordinary differential equation, the techniques of ordinary differential equation, then why do we need NC or numerical computations? So it is due to the fact that many problems in the real life, like problems of like fluid mechanics, aerodynamics, or any other field, includes values with the larger parameters and involve complicated or elusive integrals which cannot be solved by the exact methods or analytical methods. Many ODE methods and the many previous methods were failed in some restrictions or circumstances or conditions. So such problems can be solved by the numerical methods, which is approximated by the certain tools of functional analysis and the solution obtained by the numerical methods, because it is all about the real life, and real life has many problems or many parameters or factors involved in this. So it is, and the solution obtained by the numerical methods is more accurate, and by using the technique of error analysis, the solution is more convergent, consistent, and stable. So stability is really important for the validity of that specific numerical method. So the main goal of the numerical computations is to develop efficient algorithms or efficient methods for computing precise numerical values of the mathematical quantities, including functions, integrals, solutions, and algebraic equations, and solutions to the differential equations like ODE and PDE. So this is the reason that why do we need numerical computations. So we need to study the basic practical applications of numerical computations, that in which fields or how it is used in the real life. So first application of this is engineering. It can be electrical engineering, in a circuit analysis, or it can be in civil engineering, it can be a mechanical engineering. So any field of engineering. And also second application is physical sciences and the natural sciences. So in physical and natural sciences it is widely applicable, as in the computer sciences fields. Now in programming you cannot live without the basic concept of mathematics. Okay, in third, the basic field is celestial mechanics. So we use the concept of ODE numerically to study the planets, stars, galaxies, and orbital motion, planetary motion. And fourth application is the data analysis, and here we use the numerical linear algebra, basically system of linear equations. Also in the fifth one is atmospheric models. So to forecast the weather or the prediction of weather feasibility numerically is widely applicable nowadays. Also in the aerodynamics, like the computation of the trajectory of the spacecraft. It can be an aircraft, or it can be a rocket or missile, or anything like submarines. So it requires numerical solution. So basically we are concerned with the accuracy of that numerical method. Also in crash safety of cars, it requires solving partial differential equations numerically, and can improve this crash safety of cars. And also in transportation engineering, like it's all about the vehicle system. So if we study the airplane, for example, then the decision making of ticket prices, airplane crew assignment, fuel needs in airline system, it's all about solving numerically. The system is basically programmed numerically. Also in the field of civil engineering, we have to study the stiffness of a column structure, foundation design, and deflection in a beam, and also determination of a pressure in a pipe flow or pipe networks, and also vehicle density. It's all about in this field. And also the wastewater treatment is also solved numerically. So it is widely applicable to every field nowadays, because every field is now used computationally. So it is all about the practical application, practical calculations, numerical practical applications. Okay. And what is the history of this, and how it is basically how it is emerged? This field is emerged. So its history is, before the advent of mid-20th century, hand interpolation was done in large printed tables. So these interpolation formulas continued to be used as the software algorithms for solving the differential equations. So they used to solve in the large printed tables, like in the Egyptian era. It was basically it was emerged from that Egyptian era, and this concept was in the large printed tables in the form of symbols, and they use these algorithms to get the solution. And then also in it was like Greeks and Romans, and then the Muslim scientists, they used this technique, and the solution found was more accurate than the where it was failed analytically. So this is all about its practical applications and history. And then we come to the motivation of numerical computations. So basically, how will you approach to solve these problems? There are basically three ways to solve the basic problem of mathematics. So solutions can be obtained by, first method is the analytical method, second method is the graphical method, and third one is the numerical method. So there are basically three ways to find the solution of a mathematical problem. So first is analytical method. Analytical method, you have to keep this word analytical means logical. So logical methods are, you have studied before in the linear algebra or a system of linear equations, and also for the differential equations you have studied in ODE, and then in calculus these all methods were the exact method for a continuous function. So this method fails. These all methods of analytical methods or exact methods or direct methods were failed for, it is only valid for some simple or restricted conditions. But if we add the factors and parameters for the complicated equations, these methods fail. So next is graphical method. So graphical method is like we use in in the field of stats. So it requires larger amount of data, and then using that data. So this process is a quite tedious process. Okay, and so now we come to the numerical method. So although this numerical method is a very efficient method. So we approximate, because we are not dealing with the ideal situations. Now we are dealing with the real life problems. So real life problems, we just have to approximate by using the calculations, and the solution obtained by the experimenting and measurements and approximations is more accurate. So for that we have to use the error analysis for its accuracy. Okay, so this is the motivation of the numerically. Then what are the basic things we need to know, or we need to understand, that to be the method to be effective? So to provide such methods, like if you have methods, numerical methods, such methods should be efficient. So first is the method should be efficient, second one is constructive, and third one is reliable. So these methods or numerical methods should be constructive, efficient, and reliable. So if these three conditions are met, that means that your solution is a convergent solution. So that method is the most reliable, efficient, constructive method of the numerical methods. So, okay, one thing we need to study is that you have to check that any method or any problem, or any problem that we have to apply, mathematical problem is well posed if and only if it has its solution has. We have to check the solutions. So its solution should be, there are three conditions. First condition is its solution should exist. So existence is a major prerequisite condition for this. And second one is that its solution should be unique. So that is the second condition. And the third one is continuity with respect to the input data. So that is, well-posedness is all about the continuity with the input with respect to the input data. So such problem is, mathematical problem is well posed. If it is not well posed, then the problem is called ill posed. Now I will tell you about very simple definition or concept about the well posedness. Like if you apply if you make some program in a MATLAB, and you have some input changes, you just change the input. So small changes in the input gives you the small changes in the output. So that is the concept of continuity with respect to the input data. So small changes in the input gives the small changes in the output. Then you can say that your problem is the well posed problem. And also if you apply the small changes in the input data, and it gives the drastic changes in the output, so now your problem is not well posed, so it is called ill posed problem. And ill posed problems can be transformed into a well posed problem by selecting suitable substitution. So this is all about the introduction to the numerical computations. I hope that you understand this lecture, and it's a very interesting topic. So in the second lecture we will study some floating point representations and some error analysis, and all about the precision and accuracy. So thank you so much.